If you're passionate about classical education and you're looking for the next step, Hillsdale College's Diana Davis Spencer Graduate School of Classical Education is now offering 2 master's degree programs. These programs provide students with a broad philosophical, historical, literary, and pedagogical perspective on classical education. The Master of Arts in Classical Education is a 2-year, in-person program on Hillsdale's campus in Michigan, while the Master of Classical Education Leadership is a 3-year hybrid program with a 1-week summer class held at Hillsdale College. Whether you're interested in teaching, administration, or another area within the field of classical education, we're prepared to offer you a foundational, time-proven approach to your studies. We want to see your application soon. Applications must be submitted on or before December 15, 2024 for full consideration. To learn more and submit your application, visit classicalgrad.hillsdale.edu. That's classicalgrad.hillsdale.edu.
Welcome to the Hillsdale College K-12 Classical Education Podcast, bringing you insight into classical education and its unique emphasis on human virtue and moral character, responsible citizenship, content-rich curricula, and teacher-led classrooms. Now your host, Scott Bertram.
We continue our series of episodes from presentations delivered at Hoogland Center for Teacher Excellence seminars. The Hoogland Center for Teacher Excellence, an outreach of the Hillsdale College K-12 Education Office, offers educators the opportunity to deepen their content knowledge and refine their skills in the classroom. These one-day conferences are hosted during the academic year in cities across the nation and feature presentations by Hillsdale College faculty, K-12 office staff, and leaders in the Hillsdale network of member schools. There is no cost to attend, and attendees may earn professional development credits. Currently, the Hoogland Center is hosting a series exploring the art of teaching a variety of subjects. To learn more about upcoming events, please visit our website, k12.hillsdale.edu.
Well, it's wonderful to be with all of you tonight, and it's an honor to be able to speak with you. As you all know, teaching is one of the noblest arts and also one of the most difficult arts. And I don't know about you, but I always found it was this time of year, towards the end of February, and this is an especially long February, that you start to feel tired in a new way, right? It's teacher tired, and you realize this is what that word means, right? So I appreciate that all of you made the effort to come out here, knowing that you had to make extra sub-plans and probably have a stack of grading to return to. But I hope that the next couple of days will be an opportunity for rest. Maybe you can relax a little bit, learn something, and enjoy one another's company. And I hope that next week you'll return a little bit refreshed and reinvigorated. So tonight I have been asked to speak about science and the liberal arts. And when you see that topic, you might initially think that that's a misprint, that instead of and, it should say or. Science or the liberal arts, these are not sets of disciplines that usually have a lot to do with each other. The liberal artists I do know some liberal artists, they, I think, are privately grateful that their subjects have a lot to do with things like beauty and goodness and very little to do with things like calculations. But I do want to argue tonight that these sets of subjects go together, and not only do they need to be in dialogue and in contact with each other, but that they're necessary for one another. And I want to suggest that without the sciences, the liberal arts cannot, in fact, attain their purpose. And that also when science is removed from the overall vision of the liberal arts, it also becomes unmoored from its own objects of study, which is nature. So that's my thesis. Here's my outline. In thinking through these ideas, I want to think in 3 main parts. The first part, I want to look at a historical idea of the liberal arts and liberal education. I want to think a little bit about what the place of the sciences traditionally was in that whole of liberal education. Then I want to move into the mathematical revolution. Usually it would be called the scientific revolution, but I'm trying to be provocative. It's the mathematical revolution. And I want to look at the early modern period and think about how these scientists understood the relationship between math and science, and what that meant for their overall understanding of how to approach nature. And then finally, I want to look at modern science, contemporary science. I'm thinking of what has gone on in science really since the last revolution, which would be the early 20th century with Einstein and Heisenberg. I think these revolutions of science, They have a lot of ramifications for how we understand our project and how science fits into the whole of education. So first I want to look at liberal education itself, the liberal arts within this tradition of liberal education. What is it? Clearly it has something to do with freedom, right? There's no getting the liberality out of liberal education. But what does it have to do with freedom? I think often when we think of freedom, we have a notion of a kind of freedom of indifference, right? Liberal education is about a kind of freedom for excellence. It's a little bit of a deeper notion. I think, for example, of my children, right? A child is carefree. Sometimes we envy their freedom, right? They can do whatever they want, right? They have no cares. We watch them playing on the swing set or running through the field, right? But inevitably what happens is that one of them falls on their faces and they get a mouthful of dirt and they come in crying, and another one wants a snack, right? And they can't get it. And so there's this difference in freedom. They might be carefree, but because they're carefree, they also can't take care of themselves, right? And as adults, although we might wish to be carefree sometimes, it's nice that we can actually take care of ourselves, that we have the ability for excellence, right? Maybe another example, when I was 5, my parents and my music teacher gave me the choice of studying either piano or violin. And at that time, that was a freedom of indifference, right? I had a choice that lay in front of me. I could go either way. Nothing determined me to one or the other. I chose to study piano and did for a number of years, and now I can play the piano. I can't get that freedom of indifference back, right? I can never go back to that choice. I've now been determined in a certain way. I suppose I could pick up the violin, but it probably wouldn't go very well. So I don't have those options anymore, but what I do have is a freedom to play the piano now, which I didn't have when I was 5. So there's a kind of freedom of excellence, an ability to act in a certain way. So the liberal arts, the liberal education aims at this kind of freedom of excellence, right? It's meant to give us the ability to act in an excellent way as human beings. And therefore it liberates us, and it liberates us in 2 primary ways, which correspond to the ways in which we find ourselves, I guess, naturally enslaved in the human condition, right? A liberal education is meant to free us from our natural ignorance and inclination to error, and it's also meant to free us from our natural moral weakness and our inclination to vice by instilling in us virtues or moral strength. So this freedom, right, this freedom to act in an excellent human manner is not something that we possess naturally. It's something that must be gained, and therefore it's something that requires education. What would such an education and freedom look like? Well, again, freedom to be an excellent human being means that you have the ability to act for real human goods. And so a liberal education, at least, has to consist in a knowledge and love of those real goods. It requires us in a way to go out from our own little worlds of appearance and appetite and into what's real. We're free when we know real goods and when we love real goods, rather than the fictions or appearances or lesser goods that prevent us from attaining real human excellence and human happiness. So we can only be free to act in the best way that a human being can if we have knowledge of those real goods. Right? D.C. Schindler puts it nicely here in a book that has nothing to do with science, Love and the Postmodern Predicament. He says, freedom is an intrinsic participation in the goodness that belongs to reality in its very being. Freedom in this respect is always a kind of involvement in reality. So a liberal education is, in some sense, it's an education for freedom, and that also means that it's an education in reality. Right? What it aims at is the real and the highest parts of reality. Well, that's a tall order. Okay, so how do we do this? How can we educate in a way that aims at the highest realities? Well, the key, for the ancients at least, is the liberal arts. Right? So here's Hugh of St. Victor, writing in the 12th century. He says, the ancients in their studies especially selected 7 disciplines to be mastered by those who were to be educated. These, one might say, constitute the best instruments by which the way is prepared for the mind's complete knowledge of philosophic truth. Therefore, they are called by the name trivium and quadrivium, because by them, as by certain roads, in Latin via, a quick mind enters into the secret places of wisdom. So the liberal arts are not the whole of liberal education, but they play a special function, right, that no other part of liberal education can play. And their function is that they're roads, right? Hugh of St. Victor says they're roads. What makes a good road? I don't know about you, but what I like in a road is I want it to be secure and certain and safe and efficient, and I want it to start where I am, and I want it to end where I'm going. And that's what the liberal arts are meant to do as roads, and that's what sets them apart from other parts of liberal education. So the idea with these liberal arts, from grammar and logic, rhetoric, all the way up into mathematics, the idea is that they're appropriate for the beginner. Every child can do grammar at some level, but they lead you all the way to the threshold of wisdom. At the end, at the height of grammar, you're not diagramming sentences anymore. You're considering how words signify reality. If you understand how words signify the real, you're close to wisdom, right? That's pretty close. And the other liberal arts do something in a similar fashion. Not all parts of liberal education do this, right? There are some disciplines which are more noble than the liberal arts, like the study of ethics. It's more noble to study ethics than to study grammar. But ethics is not appropriate for a beginner, right? You can't begin there, and so it's not one of those roads from beginning to end. Maybe dance. It's wonderful to study dance, right? It can be a cultural thing, but there's also a very high aesthetic value, but it doesn't of itself lead to wisdom, even though you can begin it as a child, right? So that's what's special about the liberal arts, is that they're these roads that begin at the beginning and they end where you want to go. Here's a diagram of traditional sort of schematic of the liberal arts, okay? Again, notice that the 7 liberal arts here in the middle, they're not exactly the most fundamental thing, although they're close. They're also not the very end. Before you begin grammar, before you begin to analyze language, you of course have to speak the language. So it all begins with sense experience, that sensation of the world. And then the idea is that you rise through them. First, the trivium, which is grammar and logic and rhetoric. Those are the arts that have to do with the word. And then after that, you go through the quadrivium, which is the 4 arts that have to do with quantity. Here, arithmetic, geometry, music, and astronomy. Notice a couple of things about this schematic. Number 1, it's an ascent, right? We're going upwards. We're trying to attain higher beings. It's an ascent into the most real, right? The highest realities. The other thing that I think is worth noticing is that within the quadrivium within the trivium and the quadrivium as a whole, there's a sort of motion from inwards outwards, right? So you begin in grammar, and in grammar you're considering how your word signifies your thought. That's internal, right? That's in you. In logic, you're considering how the thought signifies reality. You're going out of yourself. In rhetoric, you're considering the expression of truth to others. There's this motion outwards from the inside, right? And so in that way, we're also moving from ourselves into other real things. Right? It draws you out of yourself. The quadrivium works in a similar way, and I want to spend a couple of minutes on this because clearly the quadrivium is a little bit closer to the sciences, I think, at least as we usually think of them, than the trivium. But also in the quadrivium, there's this motion from the inside outside. With arithmetic and geometry, these are things that take place in our heads, right? You can sit in a dark closet and you can make discoveries in geometry. I don't know if I want to, but you could, right? It doesn't require engaging with external reality. It begins in external reality. The first things that you know are quantities really there in the world. And we abstract those things. We take those from the matter. Right? We take the 5 from the flesh and the bone. Right? And what our concept is simply that quantity abstracted from its material in the real world. Right? And so in arithmetic and in mathematics, what you know, that quantity that you know, whether it be a line or a square or the number 5, right? That's a real thing, and it's there in reality too. And so there's this point of contact, right? There's something out there which is real. It's a quantity which has being, and that's also what's in here, and it's the same. Right? And that allows us to make a foray. Right? Quantity is maybe not the most essential thing to real beings, but it gets us there. It's a step there. Once we move into music and astronomy, as they're traditionally understood, this is again an application. So from the mathematics that takes place within us, right, then we apply that back to nature. So an example would be Newton. Right? When Newton is trying to think about gravity, one of the things that he knows from math, which takes place in his mind, is that there are mathematical connections between circles and ellipses and parabolas. Right? If there's a mathematical connection, then is it possible that there's also a real connection between those things in nature? And that one and the same cause explains orbits in circles and ellipses and also explains the parabolic trajectory of a projectile. Right? it turns out that is the case, right? That there is a single cause that explains all of those things. So there's this movement from the internal mathematics, right, to apply that to reality insofar as it's quantitative. So there's that inward-outward motion. Traditionally, we would move from the liberal arts into philosophy. I don't want to spend too long on that here, but the idea is that there's more to being than quantity, and although it might get you quite far, and you can describe the motions of things and their form in some way, there's something deeper there still to be known, and that we want to know it in what it really is, in the deepest way possible. And so that would be a step beyond what we're capable of in the quadrivium. Okay. Science, oh, that was loud, I assume would fit somewhere up here, right? They're limiting themselves to music and astronomy as the applications of mathematics, but if astronomy especially, right, the study of the stars and the planets, moving into natural philosophy where we're asking real questions about nature, what is motion, what is mass, what is time, what is space. Science is somewhere in that realm. It seems to occupy a large part of the quadrivium. A lot of what we're doing is measuring. But then it also seems to be reaching up into natural philosophy. And we're asking those questions in biology of what is life, right? And what are the causes of life? And that's going beyond sort of metric. Right? That's those what is it questions. Those are heading to wisdom. So science is somewhere in there. So in the liberal arts, we've got this grand scheme. It looks wonderful, doesn't it? Here's a picture of how wonderful it looks. This is Flammarion's engraving. You've got this grand scheme where you're sort of seeing beyond nature, beyond the physical appearances of things through astronomy, right? Poking your head through the stars, and you're seeing these amazing highest realities, these real things, the causes and the principles of the world, right? It's very grand and systematic, and there's a beauty to it. But I don't know about you, but when I think of science in conjunction with the ancients and the medievals, they made a lot of important discoveries, right? But they weren't known for scientific progress. And so you might look at this sort of schema of the liberal arts and liberal education and think, well, that sounds great, this way of getting outside of ourselves, all of this, right? But it seems that for whatever reason, it didn't, in fact, happen, right? Or at least it happened, but it didn't happen methodically. There might be a number of reasons for this. There are a lot of historical reasons, but I think there are a couple of reasons that are especially pertinent to us. One limiting factor of pre-modern science, I think, is that matter was thought to be ultimately unintelligible. Right? Here we have Aristotle telling us, the minute accuracy of mathematics is not to be demanded in all cases, but only in the case of things which have no matter. Hence, its method is not that of natural science, for presumably the whole of nature has matter. I don't know about you. I mean, we tend to think that, yeah, math is a huge part of inquiry into nature. It's the first thing that we do, right? We measure. And by those measurements, we figure out the form of the whole, and we're able to describe the whole. Right? We've brought them very closely together. But you also have to see his point, right? That when we're thinking about quantity, precisely what we do in mathematics is we abstract it from matter. We leave behind all the things that are not immediately understood, and what we're left with is the quantity, the number, the shape, which we do understand, right? And there's something that's been left behind that wasn't very intelligible at some point. So there seems to be this notion in the background that, look, matter ultimately is unintelligible. And so while we want to study the material universe and we can make progress, we shouldn't expect the precision of mathematics in the study of matter. Right? I can imagine that would do something to your drive to study the material universe. Right? If you think that ultimately you're not going to know it, then you try your best. But I would think that after a while you sort of move on and you start to study the things that do seem a little bit more knowable. Right? And I wonder if that's not a reason for the way that science was limited in pre-modern times. And this will be important later, so this principle comes back. One other limiting factor that I want to mention, this is very jargony, the traditional injunction against metabasis. Metabasis, usually a word from rhetoric, meaning a crossing of categories, right? And there was this tradition coming from Aristotle, but from others as well, that you don't cross categories, especially in mathematics, but then also as applied to the natural world. Here he says, we cannot, in demonstrating, pass from one genus to another. We cannot, for instance, prove geometrical truths by arithmetic. Now again, we might think, sure you can. A squared plus B squared equals C squared. Right? You can do that with numbers, you can do that with lines and triangles. But he has a point, again. Right? When we think about comparing quantities, can we compare arithmetic and geometry? I mean, think about what we're really doing. I don't know, what's bigger, the projection screen or 80? That's what Aristotle's getting at, right? The question doesn't make sense. You can't compare those two things. You can't move from number to a plane and vice versa. It doesn't work. If you want to compare them quantitatively, you're going to have to find some other means. Right? And we do this all the time. We talk about miles per hour. Right? But how do you compare a mile and an hour? Can you get a mile that's equal to an hour? I don't think so. Your height to weight ratio. Aristotle would say, there's no such thing. You can't compare your height and your weight. Those are two different kinds of quantity. So I think it makes sense, right? Their resistance to wanting to compare those things in those most basic questions, it doesn't seem that there is any comparison. And I think this is the reason for, when I showed you this, the sort of diagram of the liberal arts, you notice that you move from arithmetic and geometry into just music and astronomy. And you think, why music and astronomy, right? Why not physics and chemistry and biology and maybe some of those other sciences? But I think the reason is connected to this. Right? If in those sciences we're trying to understand nature through quantity, then our inquiry into nature is limited by what we can do with a certain kind of quantity. So the ancients would have studied optics. Right? Well, you can study optics mathematically because it's light. It moves in straight lines. That's geometry. Right? And all you need to study optics is geometry, and you can focus on that. Right? With music, the study of music, for them it was more harmony, right? So you're thinking about the ratios between the notes in an octave, a perfect fifth, a major third, and so on. That's governed by number, and you can just do an arithmetical analysis in music, right? And you can understand the form of music, the source of beauty, simply through arithmetic. You don't have to cross from one kind of quantity to another. Imagine the ancients looking out at the physical world and thinking, how am I going to analyze this mathematically? You've got weight, and you've got mass, and you have distance, and you have time. None of those things are comparable. So what are you going to do? You can't compare those things. So while you might make a little bit of headway in measurement, ultimately there doesn't seem to be a way, sort of a priori, there's not a way from the beginning to bring all of that together. So these are two barriers, I think, in pre-modern science to the development of science, and it's especially in overcoming these things that scientists in the scientific revolution, what I'm calling the mathematical revolution, it's in overcoming these barriers that science just explodes. And so I think the explosion of science, especially physics, I'm speaking more about physics here, but I think it comes largely from developments in mathematics. So that's what I want to look at next. Okay. So if we're moving from those ancients with their colorful vision of the liberal arts and celestial spheres, then I think we can start to look at what happens in the pre-modern times. There are many who were trying to expand mathematical arts, but the central figure is probably René Descartes. Right? And coming from this world of limited scientific knowledge, Descartes was frustrated with the lack of certainty and agreement. Right? He complains about how none of these philosophers agree about anything. It all seems to be uncertain. They're all saying things that sound halfway decent, but I can't make heads or tails of it. Right? Descartes is frustrated by this, and he wants to overcome that Aristotelian assumption that we shouldn't expect mathematical precision in everything. Descartes thinks it's not because of the things we're studying that we can't understand them, it's because we're using the wrong method. Right? So he says, among all those who had previously searched for truth in the sciences, mathematicians were the only ones who were able to find some demonstrations, i.e. inferences, which were certain and evident. So Descartes' thought is, well, look, none of these sciences, none of these disciplines have made any headway, but math has. So those mathematicians, they're doing something right. And if we could just do what all those mathematicians are doing and apply their method to every other discipline, then we would make similar progress in every other discipline, and we would have knowledge which is precise and which is certain and which can progress according to a method. But if we're going to take that mathematical, he called it a universal mathesis, right? If we're going to take that mathematical method and try to apply it to everything, then somehow we have to overcome that crossing of categories. If math is about number or quantity, how are we going to apply that method to things that aren't essentially quantifiable? So here's what he thinks. He says, "It was not my intention to try to learn all the special sciences that are usually called mathematics, for I saw that, despite the diversity of the objects involved, they all agree in considering only the various relations or proportions between the objects in question. Thus, I thought that it would be best to examine these proportions in general." So Descartes looks initially at arithmetic and geometry, and he thinks, well, you can't cross from one to the other, but is there something those two disciplines are doing in common that I could abstract even further? So not just abstracting from quantity, not just abstracting from matter, but now abstracting also from quantity. Can I just pay attention to the relationships or the proportions between quantities and get some kind of universal method? And that's, in fact, what he does. So I'm going to give you a really easy example of what this looks like for Descartes. Right? Here's an example of multiplication. This first definition is Euclid's definition. Multiplication. A number is said to multiply a number when that which is multiplied is added to itself as many times as there are units in the other. It's repeated addition, right? That's how we typically think of multiplication. So we've got 3 times 4. Well, we're going to take 3 4 times, and we're going to add it to itself 4 times, and we get 12. That's Euclid's definition. Right? Hey, it also works for 5 times 2. You take 5 twice, and you get 10. Now multiply these 2 lines together. That's what Descartes' trying to figure out, right? What does that even mean, to multiply those 2 lines together? You multiply something when that which is multiplied is added to itself as many times as there are units in the other. Can you multiply lines? What's the problem? There's no unit for one, right? So multiplication seems to be impossible here. But remember, Descartes is trying to abstract from those quantities. He's trying to see what's the reasoning, what's the relation, what's the proportion behind all of this. So he wonders if he can understand multiplication in a slightly different way. Right? Says, what if we don't consider what's proper to number in arithmetic, but just the proportions? In that case, if we look at 3 times 4, we could understand it as a proportion where the unit 1 is to 3 as 4 is to 12. So multiplying 3 and 4, you still get 12 as a 4th proportional, right? If that makes sense. So here he's changing his notion of multiplication a little bit, not considering it so much as an operation, as just a certain kind of proportion. It works here too, 4 times 5. Right? The unit is to 4 as 5 is to 20. That checks out. Okay. In general, then, he knows that the unit is to the multiplier as the multiplicand is to the product. So he deduces this proportion, which he thinks is true for all numbers, maybe for all quantities. And the nice thing is that while all quantities don't have units, they can all be put into a proportion. So now he comes back to his question of lines. Can I multiply these 2 lines? Not if multiplication is something like repeated addition, because I have no unit. But I can put lines in a proportion. Unit is to the multiplier as the multiplicand is to the product. He brings these 2 lines together, right? But he thinks, hey, still, in that proportion, you start with a unit, and I don't have a unit here, right? What are we going to do? How do you find a unit of 2 lines? Well, you might bring them together and see if there's a least common measure. In some lines there are, but not in all lines, right? The diagonal of a square doesn't have anything in common with one of the sides. They're incommensurable quantities. And so we can't necessarily find a unit of these lines. So Descartes, I imagine, after lots of frustration, says, I'm just going to make one. And he chooses a unit, right? And now I have a unit, and I have 2 lines that I'm putting in a proportion, and I'm going to get myself a product out of it. Right? And that's what he does. He draws a couple of lines. We don't have to go through this. But he's able to prove that because all of the angles in the 2 triangles are similar, he's able to get this product BD. This is kind of wild. I mean, it doesn't look like it, but it is, right? What Descartes is doing mathematically, he's not discovering things in the quantities that he's abstracted from matter here. Right? He's dealing with these lines, and he's just coming up with a unit. He's creating something new. And it's not just a little thing. He puts a unit into these quantities. That unit is the thing in virtue of which he understands all other quantities. Right? What if I had chosen a different unit here? I would get a different product. How strange is that? Right? That you can take these 2 lines that have some sort of length, and it just depends on your unit, and you can take anything you want, and your multiplication gives you a completely different result. What is that? What's the truth there? But again, for Descartes, it doesn't matter about the quantities. We've abstracted from the quantities, right? What matters is the relation. So as long as you keep the proportion same, then you're doing good mathematics. You're doing something which is even beyond arithmetic and geometry. Right? Okay, it reminds me of something that Henri Poincaré says, a scientist, but he's commenting on mathematics, and he says, mathematicians do not study objects, but the relations between the objects. It is therefore indifferent to them when the objects are replaced by other objects, so long as the relations do not change. Right? So mathematics here with Descartes is no longer really about quantity, but it's simply about relation. Okay. So here are a few key points about Descartes to keep in mind, and then we'll look at some scientists. All right. Number one, with his mathematics, he's not conflating geometry and arithmetic, but he is establishing an analogy between them. So in that multiplication of those two lines, he's not doing arithmetic there, right? He hasn't said that lines are numbers or anything like that, but he's taken something over from arithmetic and he's found out how to do something analogous in geometry. Right? So there's always a likeness here. Second, with this new method, this new Cartesian method, any quantities can potentially be understood through an analogy with arithmetic. Right? And this, as you perhaps are guessing, this is what results in the explosion of science. Right? If any quantities can be put into this analogy, then length and number and weight and time and all of those things, I don't have to come up with a mathematics of time. All I have to do is figure out a way to express the relationship between times, which is proportional to a relationship between numbers. And I get numbers, right? I know those things. So arithmetic becomes almost like an image through which you can understand other kinds of quantity, right? There's that analogy. Okay, so those are good things. Those help us to expand science, but we have to remember, for non-numerical quantities, unity is created, not discovered. And so this expansion, the universalization of mathematics here with Descartes, it comes at a price. While it is more universal and you can contain more types of quantities within it, the price is that we're putting something of our own minds in it, right? Descartes is able to understand quantity by putting something of himself in it instead of discovering something. He creates something and then says, this is what I'm going to measure all things according to. Right? He makes himself the measure of all, well, quantities. Right? One would think that it might be easy if you're mixing your mind with the things you're trying to know. It might be easy to mistake your mind for the things you're trying to know. Okay. Now maybe we think that's just Descartes and he was kind of crazy. No, it wasn't just Descartes. Although Newton disagreed with Descartes' physics, he pretty much picked up where Descartes left off in mathematics. Most people don't know about this, but he wrote a book on mathematics, Universal Arithmetic, that is spelled that way. These were lectures he gave as the chair of mathematics. And he's got this definition of number here, which, again, is kind of wild. He says, by number we understand not so much a multitude of unities as the abstracted ratio of any quantity to another quantity of the same kind, which we take for unity. So number is not a multitude of unities. 5 is not 5 ones. 5 is a ratio. And it's a ratio between a quantity and then also something that we have arbitrarily chosen, namely 1. Right? You see why that's kind of crazy? We're saying that the 5 in my hand here, and there is 5 in my hand, right? He's saying that's not really 5. If I say it's 5, it's because I'm relating this quantity to something that I've chosen to be the unit, which is one of my fingers, right? And because I have decided that that's the unit, therefore I can call that 5. If I call this the unit, then I call this 2.5, right? Number becomes this essentially relative thing, which is based on an arbitrary choice. Now, there's reason for doing that. We do that all the time, right? How long until your birthday? 14 days, 2 weeks, half a month, right? All of those might be the same because you're switching your units there. Right? But surely there are other things in nature that we shouldn't do that with. Right? Does a spider actually have 8 legs, or is it only 8 because I decided what a leg was in the first place? Right? What about when you get into chemistry? Is there actually a 2 and a 1 in a water molecule? Is it actually 2 hydrogens? Or am I just understanding it that way because I've made up the unit? Okay, so mathematics has become very much an art for Newton. And if we think back to this sort of more ancient idea of the liberal arts where quantity is this little sliver of reality that you grasp, right, and you can make something out of and use to go deeper into reality. If mathematics now is something which is, determined by your mind, which is somewhat relative, then it seems a little bit more removed from reality. We're not going towards the real, we're not going towards freedom, that original idea, but it actually seems a little bit of, it's masking it, right? Masking reality if we're not careful. Okay, so this is a little bit ridiculous, but here's what it seems to me it ends up meaning in a science class, right? We can ask something, so keeping Newton's ideas in the back of our minds here about quantity, say, all right, how do we measure velocity? We'll say, okay, well, velocity is, we're going to relate a traversed distance to the duration of the same motion. It's distance over time, right? That's what velocity is. Okay, but then how do we measure distance? Well, way back around the French Revolution, we measure distance by relating it to a length of a platinum iridium bar that is in Paris, right? This is kind of true, right? That's the definition of a meter. How do I know that this is 3 meters? Because it's 3 as compared to a unit, which is this X-shaped bar sitting over there in Paris. Right? That's a little bit strange, but we had to choose a unit and we had to agree on it. There has to be universal agreement. All right, how do we measure the duration of a motion? Well, now, by relating it to the unperturbed ground state hyperfine transition frequency of a cesium-133 atom, that's how. This is very artificial. Right? This is very artificial. Now, again, it's for good reason. It becomes universal. These are things that we can all agree upon. We've decided on these Cartesian units, and we can understand all things in virtue of them. But I remember one class where one girl in my physics class, we'll call her Alyssa, because that was her name, she stopped in the middle of class and she said, "Mr. Berndt, what are we doing?" I thought we were doing some physics, but and so I probed a little bit, and she said, "Look, you're telling me that F equals ma, but if I multiply F by T, I call it impulse, but if I multiply F by D, I call it work." And what is that? These are just different concepts, different variables. I put them together however I want, and we're saying that these are different quantities that somehow signify reality, and this is the question she was asking, right? This mathematization of physics, where we're inserting something of ourselves into it. You start to wonder, what does this in fact have to do with matter? Right? Now, we can work it out. It does ultimately come back to matter. But it's pretty unclear when you're doing mathematical physics exactly what it is you're talking about, the reality of what you're talking about, right? Okay. So in physics, what we see is the arithmetic. It's the algebra, right? But remember, that's an analogy for Descartes and Newton. What it's describing is something else which is like it, right? There's something which is force, and there's something which is mass and acceleration, and they're related to one another in a way which is like those symbols on the page, but it's not the same. It's an analogy. So you're seeing nature out of the corner of your eye, as it were. You can't quite look at it. Okay. Newton seems, in a way, to aim at this somewhat intentionally. He writes in the Principia, "Although time, space, place, and motion are very familiar to everyone, it must be noted that these quantities are popularly conceived solely with reference to the objects of sense perception. And this is the source of certain preconceptions. To eliminate them, it is useful to distinguish these quantities into absolute and relative, true and apparent, mathematical and common." Notice 2 things about that. One, he says that we understand these things with reference to the objects of sense perceptions, and we need to eliminate the preconceptions that come from that, right? So although these things ultimately come to us from sensation, we have to try to get rid of some of those things that come along with sensation. It seems right. He's seeking something which is precise. He wants something more universal, right? But there is a sort of, casting aside of those material things, the physical things. But maybe more importantly, he goes on to distinguish the quantities into absolute and relative, true and apparent, mathematical and common. If I'm right in taking that as a sort of proportion, he's equating the true and the mathematical, right? And that those things are absolute. This is a huge shift, right? So if within the framework of liberal education, we're using math as a sort of tool to reveal nature, right? To apply back to matter and then probe more deeply into what it is, Newton seems to be going kind of in the other direction, right? He seems to be saying here, at least, which, he has other quotes, but he's saying here, at least, that we're not really looking back at matter, but really we're trying to ground the truth of our science in more abstract ideas, right? Physics for Newton is not grounded in the material world as material. It's grounded in his abstract conceptions of space and time and motion. And he thinks that's the more universal and that's the more certain. That's completely different, right? That's a totally inverted notion of what was in liberal education. Okay. All right. So this is a guess, but I'm wondering here if Newton had to put up a little schematic diagram of disciplines or subjects, here's what I think he might do. Maybe if he's in cahoots with Descartes, this is what he might do. I think they get rid of sense experience because we don't trust that, especially Descartes. Right? We're not sure if that's really there. Okay. Then we also want to get rid of grammar and logic and rhetoric. Right? Descartes says they're nice to know, but ultimately we don't want to express truths in words because they're not precise enough. We want to express them in symbols through a universal mathesis. Right? Arithmetic and geometry are okay, but we need to do better, and we need to have a more universal method, which is our universal mathesis. Astronomy and music, those are okay too, but we can do better than that with mathematical physics. Ultimately, we're not trying to probe into the essence of things, really, but we're trying to get to a kind of what I'm calling mathematical metaphysics. Right? What Newton wants to understand is space itself, which he considers to be the most ultimate reality. He actually calls space the quantity of the existence of God. So for him, that is the most real thing. Right? The most abstract, the most absolute is the most real. Okay. Well, one way or another, although I find this a little bit disturbing in some ways, and I'm not sure if I really have 5 fingers anymore, Newtonian physics is successful, right? And although I think some of the principles are questionable, for 200 years, physics expands and it grows and it develops, right? Wildly successful. Newtonian physics eventually could explain all of mechanics. It came to encompass electrodynamics and eventually thermodynamics. Most people thought science was basically at the end. We just have to work out all the details, right? There's the famous Pierre-Simon Laplace's little story about the demon. Do you know Laplace's demon? I don't know why they call it a demon, really, but he makes the claim that if some being were to know every particle in the universe and its momentum, you would know the entirety of the future, right? So everything is determined by knowing those things, the matter, the momentum. Okay. So all of that expands drastically through the scientific revolution, right? But at the root of this, all of classical physics is ultimately based on Newton's mathematizing of the fundamental physical realities, right? He mathematizes matter and space and time and motion. If the universe is really mathematical all the way down, right? If it's really mathematical all the way down, then there should be no limit to the power of classical physics to explain it, right? But that is what was put to the test at the beginning of the 20th century, I think. That's when we were actually in a position to study the fundamental realities themselves, to ask what is space, what is time, what is motion, and that's when we started to see some cracks in the picture. Okay, so looking here a little bit at modern physics. The first crack we see comes through relativity with Einstein. Right? We know how this came about. Experiments that were performed by Albert Michelson and Edward Morley in 1887 showed that the speed of light does not vary with respect to a medium. Right? Okay, so the velocity is constant with respect to a medium. We also saw, through observations of binary stars, Willem de Sitter, right, was able to show that the speed of light also doesn't vary with respect to its source. Okay? So if it doesn't vary with respect to a medium and it doesn't vary with respect to a source, we're kind of out of options. Right? Option C, none of the above. Right? So the speed of light c is constant in a vacuum regardless of one's reference frame. That's what we figure out with experimental physics. Why is this a problem? Here's a little example, way oversimplified. Right? Okay, so here's Albert, and he's walking on a train car. Right? He's walking at 2 meters per second. The train car is moving at 6 meters per second. Right? Okay, well, how fast is Albert moving relative to the ground? 8 meters per second, right? In 1 second, how far has he gone relative to the ground? 8 meters, right? Good, we're fine with that. What if we think about this problem relative to the train car, right? How fast is he moving? 2 meters per second. How far has he gone after 1 second? 2 meters. Okay, that's all fine. Notice that the two observers disagree about the velocities, but that's okay because they also disagree about the distances. Right? There's one time which remains the same, and we can all agree that the proportion is the same. Okay. So we figure out that when observers disagree about the measurement of distance, they also have to disagree about the measurement of velocity. But here's the problem. With light, all observers agree about the measurement of the speed of light, even when they disagree about the measurement of the distance it traverses. Right? This is a mathematical problem. It's also a science problem, but it's mainly a very simple algebra problem. You can't disagree about distance, keep time the same, and somehow agree about velocity. That's bad algebra. The Cartesian universal mathesis doesn't look like it's working suddenly. Okay. Einstein, of course, is able to solve this very cleverly by pointing out that there is one other way that you can agree about the velocity and disagree about the distance. And that's if you're willing to disagree about the time, right? And so, yes, one observer can say that he's walking at 8 meters per second, he traverses 8 meters in 1 second. The other person can say, yes, he's moving at 8 meters per second. He traverses 2 meters, but he thinks that only 0.25 seconds has passed, right? Why is this important for us here? It's important because Newton's idea of absolute time is a fiction, according to Einstein. Before the advent of the theory of relativity, it had always been tacitly assumed in physics that the statement of time had an absolute significance, i.e. that it is independent of the state of motion of the body of reference. But if we discard this assumption, then the conflict between the law of the propagation of light in vacuo and the principle of relativity disappears. So physics is in trouble with Einstein. Right? With Newton and Descartes, we take out the grounding in sensation. Right? That's no longer where we ground physics. Rather, we ground it in the universal, the abstract. But now Einstein comes along and says, those things aren't real either. There is no universal absolute space. There is no universal absolute time. All we're left with is this horizontal band of mathematical physics, where everything is internally consistent, but there doesn't seem to be a grounding. Right? Okay. That puts us in a pickle, right? But Einstein has also done something for us. Right? He still sees that math is a kind of image, but he's no longer deceived by it, as Newton seems to be. It's no longer an illusion. And so in that way, he sets up the possibility, perhaps, for physics to be regrounded. And so that's what happens in the other part of this last scientific revolution, right, with quantum mechanics. We see this kind of regrounding. So at the same time that Einstein was rethinking physics at the macroscopic level, quantum physicists are rethinking it at the microscopic level. And in their attempts to measure the smallest things, they repeatedly encounter mathematical contradictions, right? Those are of numerous sorts, but the most well-known is the particle-wave duality. When we shine light through a double slit, it interferes with itself on the other side, and it looks like a wave. When we bombard metals with photons, electrons come off, and there's a direct proportion between the photons and the electrons, and it looks like light is a particle. Can light be both a particle and a wave? No, because that's a contradiction. Particles are mass which moves. A wave is the transference of energy without the mass moving. Right? Those two things can't be true at the same time. So here's what Dirac says about it in the Principles of Quantum Mechanics. All material particles have wave properties, which can be exhibited under suitable conditions. We have here a very striking and general example of the breakdown of classical mechanics, not merely an inaccuracy in its laws of motion, but an inadequacy of its concepts to supply us with a description of atomic events. Right? Okay, so classical physics no longer holds at this level. For many years, physicists tried different mathematical models with no success. They got more contradictions. And they only started to make success when they asked if maybe what they were studying might in fact be beyond mathematics. Here's Heisenberg saying, "Is it true, perhaps, that only such experimental situations can arise in nature as can be expressed in the mathematical formalism?" The assumption that this was actually true led to limitations in the use of those concepts that had been the basis of classical physics since Newton. So what is Heisenberg saying? He's saying there's a limit to mathematical analysis of matter. There's something down there in matter, and we can't get further than that with our mathematical models. Here's his mathematical model, right? His principle of uncertainty. We don't have to talk about it too much here, but these are two terms, right? Delta Q prime and delta P prime, which represent uncertainty. They're symbols of how uncertain we are about position and momentum, respectively. Now, most people thought, well, if you're uncertain and you're trying to be more certain, then just measure better. It's a problem with your instruments. Heisenberg points out, no, when we multiply these two things together, we get a constant. It's Planck's constant. that can't be an accident. If this is a problem with measurement, then we should be able to do a little bit better, to get a little bit more precise. But what the math is telling us is that math itself is limited. I imagine it like a little, half-filled balloon, and there's something in there I'm trying to know, right? And when I try to get at it from one side, the other side expands a little bit, and I know less on this other side. And when I try to get it from there, I know it better there, and then I know it less on this other side, right? So there's a sort of maximum knowledge that you can have of material particles here. Okay. For someone like Laplace, this is impossible. Classical physics assumes that the universe is mathematical all the way down, and that math can always make sense of matter. But quantum physics puts us firmly back into what looks rather like an old Aristotelian picture. And we find ourselves having to admit with Aristotle that finally we should not expect mathematical precision in the whole of nature. So what do we do? If we've come to an end of our mathematical analysis, right, how then do we approach nature if mathematics isn't the whole? Einstein and Heisenberg both give us a little clue here, which is what I'm going to end with. Einstein says, fundamental ideas play the most essential role in forming physical theory. Books on physics are full of complicated mathematical formulae, but thoughts and ideas, not formulae, are the beginning of every physical theory. The ideas must later take the mathematical form of a quantitative theory to make possible the comparison with experiment. In other words, math is not the only method of knowing nature, even if it's a central one. Right? We also have to approach nature through other means if we're to know it fully. First through sensation and common experience, then certainly through math and analysis. And then finally, we can ask about its causes and the essences that are there. Heisenberg says something similar. One of the most important features of the development and the analysis of modern physics is the experience that the concepts of natural language, vaguely defined as they are, seem to be more stable in the expansion of knowledge than the precise terms of scientific language, derived as an idealization from only limited groups of phenomena. This is in fact not surprising, since the concepts of natural language are formed by the immediate connection to reality. They represent reality. So again, the initial ideas, the common experience, are the connection to reality. First, we have sense experience. Then we have the study of nature through words and language. And then we arrive at quantitative analysis. So in other words, I think what we have with modern physics is something a lot like this. Einstein and Heisenberg are telling us, start with sense experience, start with common experience, because although that might be imprecise and undefined, it gives you a knowledge of nature that mathematics can't. And beyond that, move into language, right? Consider nature through language, because again, although it's undefined and vague, that's the real connection to reality. Then yes, give a mathematical treatment, and don't go back to the ancients with the mathematical treatment, right? Expand away from arithmetic and geometry, expand away from music and astronomy into a real mathematical physics, and then we can have a complete picture, a more complete way of knowing nature, right? So, it seems to me that modern physics, through both relativity and quantum theory, has shown us that the early methods of Descartes and Newton and others, while powerful and necessary, aren't complete, and eventually they undermine themselves. Right? And what's needed for a true study of nature seems to be a reintegration of our different ways of knowing nature. So we don't simply go back, but we also don't simply reject. From the moderns, we have mathematics. From the ancients, we have common experience and ideas grounded in reality. So if I may, I'll end with a little bit of an exhortation. I think all of this puts us at an exciting place in science education. You and I are in a position in science that I don't think anyone has been in before. We have all of modern science at our disposal, all the power of mathematics. We don't have to be confined by the misconceptions of the ancients. But at the same time, we've also seen the pitfalls of concentrating too much on classical physics, of mistaking our minds for the objects they study. And we have the knowledge and the means to avoid it, right? And so, if I'm not mistaken, I think we're actually in the position that to study science in a way that it orients us towards, again, true human freedom, and ultimately towards what's real. So, those are some thoughts. Thank you.
If you enjoyed this lecture, we encourage you to visit our website, k12.hillsdale.edu, for additional information on upcoming Hoogland Center events and other free resources for educators.